if you read this down here, you know, yeah, we have a matching procedure with our pattern, typically a ball or a curl. We could also take a box, whatever you like. And then we put it everywhere, we expand it, put it everywhere, go over the field and do a lot of calculations. Of course, we can do that in parallel, but still a lot of work. But once again, computer scientists believe a working computer is a good computer, working people are bad people, right? Or lazy, or people who are not stupid, are too stupid. So we give them all these tools, get some of their money, right? They have less work, we're going to be rich, and the computer scientist is going to be happy, right? That's the deal. Yeah? So pretty much the idea here once again, don't worry too much about the computer working a lot. We can look later for being more efficient. Yeah. And now, if you're image processing, then you know that moments, yes, statistical moments are one of the ideas that we could use to find a pattern once again. And yeah, moments are projections onto a basis in a function space. Yeah, that's as well known in image processing. There's a lot of stuff that you can read, and we also were in contact with some people from Prague, for example, who do a lot of research here. And here we have some simple monomial vector field bases. How are the basis elements looks like? It comes out from the theory automatically. Yeah, so don't worry too much about that. And yeah, you have to be invariant under certain transformations, and the idea is, yeah, you calculate the moment variance by putting pattern and field in a predefined standard position. Yeah, and because I know that all my moments, if I move it, if I rotate it and so on, are changing in a certain way, so I can take a few of those and calculate the actual translation, the scaling or the rotation, and then change all the others, and then compare the others, except for the ones that I used to calculate, to see which transformation was applied. That's once again a trick that we just borrowed from image processing. This is well known. Yeah? But it also works for this vector value, so we can also take care of this additional rotation because we have a vector field or not a multiple scalar field or color image. Yeah? And the other moments are transformed and serve as invariants because once you transform them and normalize them, they are invariant. They will be the same no matter if the flow goes like this or like this. You only have to have a lot of, so if the flow is very, very simple, yeah, then you may have a problem because all the other variants are going to be basically zero. Yeah? But in a realistic data set, you're not going to be worried about having just 3 values. So, yeah, if that's the original flow, if I normalize with respect to translation, so I'm subtracting here a certain vector translation, I have 2 translations. Here I can move that part along in the image, but I could also subtract a component of the vector. Yeah, that doesn't make sense in color fields because it would mean I subtract a certain color, but sometimes if I have a vortex rotation, yeah, and superimpose on that movement in this direction, yeah, then I won't see actually the nice vortex pattern because I see a mixture between the rotation motion and this translational motion. So I can subtract that translational motion and still see there is a vortex, but it's not appearing in the way I would like it. And then it's up to you. Do you want that correction or not? We'll see that later. Okay? So translation here means outer translation, so we'll look at just as the vector field. Of course, we look at all positions, which would be the inner translation. You can normalize with respect to scale, basically just changing the norms, and then I also can rotate it. And now here is a famous example that everyone in fluid dynamics will know. It's the common vortex treat. You have a small cylinder or a circle. That's an obstacle. You have laminar constant flow coming in. It has to go around that obstacle, and you have the famous vortex shedding. So the vortex released on one side and then on the other side, and it's fluctuating, and you are traveling to the back. And there are lots of vortices here, but they don't look like actual vortices, because you have that strong motion in this direction, and have to subtract it so that you actually see it. If I take away the average flow, just average all vectors, it looks a little bit strange over here, I agree. But then you can really nicely see this rotational motion. And if I would do now an animation, these guys would be traveling quite nicely. Yeah, I think I even have the video so. Okay, and I want to find these vortices here. That's why I have to take care of this abstraction, which is once again something that you wouldn't consider in a color image. Yeah, I want to make this clear because you understand how to do moments, pattern matching based on moments in image processing and color images, and we just apply this here to vectors. In a certain area it's different, but the basic idea is the same. Yeah, you just adapt your mathematics, your algorithms, and then you go. And here now was our idea, okay, let's take an area, just take one out, and then calculate everything that's similar with respect to that very motion where you have that saddle and that critical point there. And you can see, yeah, this is the similarity, of course. Yeah, these are the ones that are kind of traveling, but I also have some other similarities. Yeah, I get some weaks over there as well. We know that. Yeah, if you do pattern matching, at some point you have to decide, is this still a pattern or is it not? Yeah. And I can also take this whole double feature or even make a larger one. Yeah. Of course, oh, I was supposed to show that movie, maybe I skipped that, I show it later. But basically, I can show that we can of course do that for each time step, and then the circles would nicely travel with the flow. And here now I have an ellipsoidal vortex, so it's a little bit stretched. And that's the image that I'm actually analyzing. There's a strong jet going in here, and you have some rotational motions there. And that's what's coming out if I really normalize with respect to removing the constant, look for rotations and scaling. If I say, well, I actually don't think that these are vortices in this connection, or for the physicist, I just kind of fix the observation and say, well, I just want to see those vortices, and there is no vortex, so there should be no similarity. Then I put that away, just take that normalization with respect to that one out, and then you see what you expect, right? Nice motion here, some similarity here. It looks the same, but the rotation, of course, goes the other way. Yeah, and then also, of course, there is some scale invariance, and then you get the pattern that you, as a human observer, would kind of find. Yeah, and of course, once again, yeah, if you come up with some other kind of symmetries or translations and invariance measures, we could do that as well and put it in. Yeah, just normalize a little bit more, basically. I can do that in 3 dimensions, basic fields. Yeah, we'll check.